Welcome back, deep divers. Today, we're pushing the limits, going way back to when the universe was just a baby.
Only about 600 million years old.
Yeah, practically a newborn. We're diving deep into a research paper all about, get this, a galaxy nicknamed Firefly Sparkle.
It's a fitting name, you'll see.
So you're the expert at unraveling these early galaxies, right?
I try my best.
Well, tell me, how do we even find something like the Firefly Sparkle out in the vastness of space?
So picture this, a magnifying glass, but in space.
Okay, I'm picturing it.
That's basically what we use. It's called gravitational lensing.
Right, I've heard of that.
A massive object, like a galaxy cluster, bends and magnifies the light from things behind it.
So the cluster acts like a lens.
Exactly. It lets us see these incredibly faint and distant galaxies.
That's amazing. It sounds like we got pretty lucky with this lensing.
Oh, we did. So what does this Firefly Sparkle look like?
That's what I want to know.
In the telescope images, it looks like a thin arc.
An arc.
Yeah, and inside this arc are 10, count them, 10 distinct star clusters.
Sparkling like fireflies.
Hence the nickname. Figure 1 in the paper actually shows it, plus 2 nearby galaxies.
Sure, yeah.
The researchers called them Firefly Best Friend and, wait for it, Firefly New Best Friend.
That's too funny. Okay, so we have this distant arc-shaped galaxy, 10 sparkly clusters.
Yeah.
What makes Firefly Sparkle so unique? Besides the name and the friends, I mean.
Well, it's like a baby picture of the universe.
Ooh, I like that.
We're seeing a young galaxy, tons of gas, just starting to form.
Fascinating.
One strange thing, though, it doesn't emit a strong Lyman alpha signal.
Hold on, back up for a sec. What's that?
Think of it like this. Young stars emit UV light, right?
Right.
When that light hits hydrogen gas, it makes a specific glow.
A cosmic beacon.
Exactly. That's the Lyman alpha signal.
So we usually see it in young galaxies.
Yeah, but Firefly Sparkle is hiding it.
So it's like it's trying to shine, but there's a cosmic fog.
You got it. Maybe the surrounding environment is super dense or dust is blocking the light.
But we can still see those star clusters you mentioned.
Oh, yeah, and this is where things get really cool.
Tell me everything.
These clusters, they're incredibly dense, way denser than the ones in our Milky Way.
Really?
Yeah, like packed cities of hot, young stars. You can even see the density difference in Figure 3b.
Wow. I'll have to check that out.
And get this, the combined mass of those 10 clusters is almost half of Firefly Sparkle's total mass.
So they're like the galaxy's foundation.
And they're unlike anything we see in later galaxies.
This is incredible. You said these stars are young and hot, but how do scientists figure that out from light that's traveled for billions of years?
We analyze the light using 2 techniques, spectroscopy and photometry.
Big words. Break it down for me.
Spectroscopy is like a fingerprint of the light, tells us its composition.
So lots of hydrogen and helium means young stars.
Exactly. Heavier elements take time to form through star life cycles.
And photometry.
That measures brightness, which tells us things like temperature and distance.
It's like cosmic detective work. What clues did they find?
Now, this is where it gets interesting. Remember that central star cluster?
Yeah, the brightest one.
Its spectrum is full of what we call nebular emissions.
Like those colorful nebula clouds.
Yep, clouds of gas and dust.
What do those emissions tell us?
They show a very low metallicity.
Meaning?
Very few elements heavier than hydrogen and helium.
So, young stars confirmed.
Oh yeah, incredibly young. And there's more. The spectrum also tells us the gas in the cluster is very dense and the electrons are super hot.
So not just young, but massive stars.
Exactly. Much larger than we expect in later galaxies. We call this a top-heavy IMF, or initial mass function.
IMF, that sounds complicated.
Think of a stellar nursery, right?
Okay.
Usually you'd see a mix of star sizes, smaller ones more common.
Right.
But with a top-heavy IMF, it's like the nursery is full of superstars, way bigger than we expect.
So Firefly Sparkle has some of the earliest stars, and they're massive giants.
It really changes how we think about the very first stars.
I can imagine. This is amazing. But what does it all mean? How does Firefly Sparkle fit into the bigger picture of galaxy evolution?
Well, remember those dense star clusters? They might be the key to understanding how galaxies like our own Milky Way formed.
Okay, you got me hooked. Tell me more.
So, the prevailing theory is that galaxies like our Milky Way, they formed from merging smaller, clumpier structures.
Of building blocks.
Yeah, exactly. And Firefly Sparkle, with its dense clusters and, well, unusual composition, it might be a snapshot of one of those early building blocks.
Like a piece of the Milky Way's baby picture.
A perfect way to put it. And those dense clusters, they could have had different fates.
Oh, Like what?
Some might have become globular clusters.
I've heard of those.
Those ancient groups of stars orbiting galaxies, like, I don't know, fireflies around a lamp.
That's a great image.
Yeah,
But not all the clusters had such a peaceful ending, right?
right. Some were probably ripped apart.
Ripped apart. By what?
Gravitational forces from merging galaxies?
Ouch. So they were scattered into space.
Basically, it's like a cosmic demolition derby.
With gravity as the wrecking ball.
Exactly. I'm guessing you're thinking some clusters might have survived and become something else.
That's what I was thinking, yeah.
Well, you're right. Some might have pulled in gas, fueling more star birth.
So they became even bigger?
Potentially. Yeah, maybe the seeds of larger structures. It's like those clusters had multiple lives, always changing as the universe around them evolved.
That's incredible. It brings us back to those massive stars in Firefly Sparkle and, their connection to the very first stars.
Right. It's mind-blowing to think about.
It really is. So if Firefly Sparkle has a top-heavy IMF, meaning more massive stars than we'd expect,
Mm-hmm.
could it be that the very first stars, after the Big Bang, were also these massive giants?
It's definitely a possibility. Could rewrite our understanding of cosmic history.
Instead of stars gradually getting bigger over time, maybe the universe started with a bang, literally. Fireworks, giant stars lighting up the darkness.
I love that analogy. But why were these first stars so massive? What was different back then?
Yeah, what were the conditions that made these behemoths?
Well, one idea is that the early universe was chemically simpler, mostly hydrogen and helium.
The lightest elements.
Right. No heavier elements to kind of put the brakes on star formation.
So no heavier elements to cool those gas clouds, which would have made smaller stars more likely.
Exactly. So the clouds back then were hotter and more massive, leading to, well, mostly giant stars.
It's like the universe started with a clean slate, and these massive stars were the first bold strokes.
Beautiful way to put it. But these stars, even though they lived fast and died young, they left a mark.
How so?
When they exploded as supernovae, they scattered heavier elements.
Enriching the material for future stars and planets.
They were creators and destroyers, forging the elements that would eventually lead to life.
That's a pretty amazing cycle. And they didn't just create heavier elements, they also played a role in reionization, right?
You're absolutely right. Remember, the early universe was filled with neutral hydrogen, blocking light.
Like a cosmic fog again.
Exactly. The light from these first stars started to ionize that gas, turning on the lights in the universe.
Making it transparent.
Yes. It's like they ripped off a blindfold, revealing the universe as we know it.
Wow, those short-lived stars had a huge impact. But going back to Firefly Sparkle and how galaxies formed, the researchers have an interesting theory, don't they?
They do. It's not just about gas slowly forming galaxies. Firefly Sparkle, with all those clusters, suggests early galaxy assembly was more like I guess you could say, a cosmic merger frenzy.
A merger frenzy.
Like a bunch of star groups, each with their own gravity, all coming together in a grand cosmic dance.
So those dense clusters weren't just passengers, they were shaping the galaxies they were in.
And some clusters might even be remnants of even smaller, more ancient galaxies.
That merged to create Firefly Sparkle.
Exactly. It's a fascinating idea. Suggests the building blocks of early galaxies were even smaller than we thought.
Like a puzzle with tinier pieces.
Exactly. It changes our picture of the early universe. It wasn't just a smooth transition from gas to stars to galaxies.
More like a wild mosh pit. Clusters slamming into each other, making larger and larger structures.
You're getting it.
Mm-hmm.
But we have to acknowledge the limitations of what we know. The researchers themselves point this out.
Right, they're honest about that.
Our understanding of stellar evolution and galaxy formation is still developing. What we see with Firefly Sparkle could be unique or it could be common.
We just don't know yet.
Exactly. It's like finding a hidden door and wanting to know what's behind it.
What other mysteries are hiding in those early galaxies? I know there's one tool that could help us find out. ALMA.
Ah, yes, the Atacama Large Millimeters of Millimeter Array.
What could LMA tell us about Firefly Sparkle?
ALMA is perfect for studying cold gas and dust, the raw materials for star formation.
So like we've seen the skeleton, the stars, and clusters.
But we need to understand the muscles and organs, the gas and dust.
So LMA could reveal how Firefly Sparkle formed and how it might change.
Exactly. How much gas it has, how it's spread out, if it's pulling in more gas.
We could even figure out the fate of those dense clusters.
Will they survive, be torn apart, or reaccrete gas and become something new?
Like peering into a crystal ball, trying to predict the future of this ancient galaxy. These are big questions. Do you think ALMA will have the answers?
ALMA is amazing, but it can't tell us everything you know.
Right, it's not a time machine.
Exactly. We can't predict the future for sure, but
We can get closer.
we can use the data to, refine our models, test different scenarios.
Like running a simulation.
Yeah, tweaking things, seeing what might happen to those clusters over billions of years.
It's fascinating. And as we've been talking, one thing that's impressed me is how the researchers are really upfront about, what they don't know.
Oh, absolutely.
They're honest about the limitations. It's refreshing.
I agree it's a sign of good science, not pretending to have all the answers.
Right, they're presenting the findings, the uncertainties, and suggesting what to research next.
It's like they're saying, here's what we know so far. Come help us learn more.
I love that. It's inviting everyone to be part of the discovery,
And that's what's so great about this field. We're always pushing the boundaries.
challenging what we thought we knew, rewriting our understanding of the universe.
And with telescopes like James Webb and LMA, we're in a golden age of astronomy.
I can't even imagine what discoveries are waiting for us.
It's truly exciting.
Well, listeners, we've covered a lot today, from the discovery of Firefly Sparkle
To those dense star clusters.
and even the nature of the very first stars.
It's been quite a journey through the early universe.
And we've only just scratched the surface of what this tiny galaxy can teach us.
Firefly Sparkle has lived up to its name, wouldn't you say?
Oh, absolutely. It sparked our curiosity and our imagination.
It's a reminder that even in the vastness of space,
Even in the faintest light from billions of years ago.
we can find clues that unlock huge truths about our universe and our place in it.
So keep looking up, keep asking questions, and never stop exploring.
Until next time, deep divers.
Keep diving deep.